All right, so I'll start the recording from here. So what was it? So sorry, go back to our picture. X12, X13, X14, X12, then X23, X25, and then X43, X46, then X43, X46, then X35, X36, and then X56, X57, and then finally X67. Okay, these are all the variables. Okay. Yeah. Right. And the shortest path, okay, we'll just call it the shortest path. Right? What we'll do is we'll take the coefficients from here, right? So, that coefficient is 4, I think, right? So 4, 7, 5. That's coefficients there. 4, 7, 5. Oh, sorry. 4, 7, and and 5. Then 3. 2, 3, 2, 5. 2, 3, 2, 5 is 3, 5. 3, 5. Then 4, 3, 4, 6. 4, 3, 4, 6. Oh, sorry. 4, 3, 4, 6 is 1, 8. 1, 8. 3, 5, 3, 6. 2, 6. 2, 6. Okay. 2, 6. And then 3, 6, and 2. 3, 6, and 2. Okay, and of course, we'll take some product of these, right? Some product of the coefficients with our variables. Okay, so that is the, this is the objectives. Now, so that's the objectives. We want to minimize the shortest path from 1 to 7. Now, how do I put in the constraints? Well, each node has a constraint. For each node, there's a constraint. So, node 1, start with node 1, and go all the way to node 7. Each node has a constraint, that's 9. Okay. Now, how do I write the constraint? Well, first for node 1, see, we have to start from node 1 and go to node 7. So we have to choose one of these, either 1, 2, 1, 3, or 1, 4. So how do I write that? Well, x12 plus x13 plus x14 must be equal to 1. Since these are binary variables, either 0 or 1, that will force one of them to be equal to 1. The others will be 0. Okay? Think about it. These take only values 0 or 1. So if I make that equal to 1, only one of them can be equal to 1. Okay, so the first constraint, node 1, is that one of these has to equal 1, is equal to 1. Yes? Let me also just put these across here. Oh, there's one extra here. Okay. Now, what about intermediate constraints? Well, okay, now let's look at node 2. So if I choose 1, 2, then I have to choose one of 2, 3, or 2, 5. If I don't choose 1, 2, I cannot choose the other. So how we write that is, what we'll take is the incoming minus the outgoing should be equal to 0. So if the incoming is 1, any one of them is 1, then one of the outgoing has to be 1. If the incoming is 0, the outgoing also has to be 0. Okay? Very simple type of constraints. So we'll take incoming minus outgoing. So or what do you want? Incoming minus outgoing or outgoing minus incoming? Okay, incoming minus outgoing. Okay. So incoming is 1, 2 here. Outgoing is 2, 3, and 2, 5. So minus 1, minus 1. And that has to be equal to 0. Right? Because if the incoming is 1, then the outgoing, one of the outgoing has to be 1. If the incoming is 0, both of the outgoing has to be 0. Similarly, incoming in at node 3 is 1, 3. outgoing are these two. So -1 here, -1 here. Now incoming at node 4 is this, outgoing is this and this. Okay. Incoming at node 5, yeah, okay, there are two incoming at node 5. 2, 5, oh, 4, no, 4, 5 is not there now, 3, 5 is there. Okay, and outgoing is 5, 6, 5, 7. Incoming at node 6 is this one, 4, 6. And outgoing is node 3. Oh, sorry, this is also incoming at node 3, sorry. Incoming at node 3, outgoing. Okay, this is incoming. Okay, node 4, incoming is 1, 4, and 1, 4 only, okay? Incoming at node 5 is 2, 5, 3, 5, outgoing is 5, 6, 5, 6. Incoming at node 6 is 4, 6, 3, 6, and 5, 6. Outgoing is 6, 7. And then at node 7, one of these two, 5, 7 or 6, 7, has to be equal to 1. Okay, so intermediate constraints are all 0, and the initial origin and destination constraints are all 1. Okay, very, very simple, no? Okay, of course. I will ask in a moment. Let's finish the problem. Oh, what happened? Data. Okay, solver. We want to minimize this. Okay, these are the variables, and all the constraints are of the same type, so equal to these. Okay, and we can solve it. All right, it's simple. 13. What did they get here? I think also 13. Huh? 13. Oh, here's 12. Okay, change the problem there. Okay, and 13. Yeah, 14. I got 13 just now. Okay, let's see. So from 1 we go to 4, 4 we go to 3, 3 to 5, 5 to 6, and 6 to 7. So, 13, yeah. Okay, quite simple. 1, 4, 3, 5, 6, 7. Yeah? So, which do you think is easier? The graph method, that labeling method, or which one? Simplex method. But, okay. It depends. Okay, this problem is simple because it's small. But I suppose still both are equivalent in a sense. Because even there you'll have lots of intermediary calculations. So, but I think, yeah, simplex method or the linear programming method definitely gives a different way. Now, by the way, this same type of problem is in what is called PERT and CPM. Any of you have come across PERT and CPM? You studied in project management, actually. So project planning, instead of looking at the shortest path, they look at the longest path. And a similar technique can be applied there. Oh, hi. Just have a little water. Right? Yeah? Oh, you. Okay, so a similar method can be applied there. Instead of, and even Dijkstra's method, instead of taking smaller values, you take the larger values. So the same Dijkstra's model is, or algorithm is used for finding the critical paths. So-called. Anyway, I've put in the slide in that LMS, I think. So, but it's not technically part of ours. But for those interested, you can have a look at that also. It's also a very useful way of applying this. Okay, so that was the shortest path problem. Okay, so now another interesting network problem is called the minimum spanning tree problem. Did we discuss this last time? We didn't, huh? Teaching similar classes, it's very confusing at times. Okay, anyway, I think with the other batch I taught this, anyway, doesn't matter. So, what do we mean by a minimum spanning tree? Well, first of all, a tree is a set of connected arcs that does not form a cycle, okay? A connected acyclic graph, a connected acyclic graph is called a tree. Now, in basic, some graphs, of course, are not trees. If a graph is not a tree, sometimes we want to look for a spanning tree. A spanning tree is a tree that connects all the nodes of that network. So suppose we have a network. A spanning tree is a sort of subgraph of the original graph in which we have connections between all nodes, and it's a tree. In other words, there's no cycle. Now, why is this useful? Well, for example, telephone connections or whatever, basically a spanning tree is like an emergency network. A network that if it fails, for example, then we're not able to connect everyone. So we want to have at least one emergency network that is live type thing. That does never fail or never fails type thing. So that's why, in a sense, how to design or how to identify a minimum sort of spanning tree where this is the sort of network that must be sort of preserved type thing. Anyway, so here in the minimum spanning tree problem, we want to determine the minimum sum of arc lengths necessary to connect all nodes in the network. So we have a network, each arc has a weight. We want to find the minimum weightage of a spanning tree, a network tree that connects all nodes in the network, subset of the original tree. So the criterion to be minimized need not just be distance. So it could be distance, it could be things like cost, it could be things like closeness, right? How closely connected they are, how important a particular network is, how important a particular connection is. Like, for example, if we're looking at, I don't know, in a city, for example, then you may want at least the connection to the police should be like that, something like that. So other criteria could be time, cost, and so on. Right? So it all depends how you. All right, now the algorithm is very simple. It's called Kruskal's algorithm, and it's really it's like what is called a greedy algorithm. Any computer science students? Greedy algorithm? You must have heard of greedy algorithm. Yes, greedy algorithm means choose the closest one at every point of time, and that's what it will do. And it turns out that this works the best also. Okay, arbitrarily begin at any node and connect it to the closest node. So take any node and look for the closest node to it. Yeah? The two nodes are referred to connected nodes, and the remaining nodes are called unconnected. Okay, so at any point you have a connected set and an unconnected set. Then identify the unconnected node that is closest to one of the connected nodes. And if they're equal or ties, then we just choose any one of them. Add this new node to the set of connected nodes and repeat until all nodes have been connected. All right, so we'll have n-1 iterations. If there are n nodes, n-1 iterations. So, for example, here, okay, let's start with node 1. Okay? May as well start with node 1. Okay, so node 1 is connected only to nodes 2 and 3, correct? So we choose the one which is closest. Node 2 is 30, node 3 is 45. So which one do we choose? Node 2. So now the connected nodes are 1 and 2. All the others are unconnected. Now look at the one that is closest to 1 or 2. This is 45, this is 25, 35, and 50. Which one is closest? 25. So connect this 5 with this, and now the connected nodes are 1, 2, and 5. Okay. Now what is closest to 1, 2, or 5? Well, this is 45. This one is 35. This one is 50, 15, 40, and that's all. Okay. So which one was least out of those numbers? 15. So connect 7 to 5. Then look at again which one is closest. So here is 30, here is 50, here is 40, here is 20, no, these are not connected yet, and that's of course 45. So 20 was least out of those. Okay. Then 10 gets connected next. I think next 8 gets connected to 10, and then you'll have, okay, now this is open some new ones, 40, 35, 40, and 45. So again, 35 becomes least, so 6 gets connected there. Now you'll have 30, 20, 45, and 45. So 20, so 3 gets connected to 6, and then 30, and then 45. So everything gets connected like that. Okay, so of course they've done it also step by step here. So first is take node 1 as my initial node, and the closest node is 2, distance 30. So connected nodes are 1 and 2. Same thing there. Then next node closest to 1 or 2 is 5, which is a distance of 25 there. Okay, so now 1, 2, 5. Next one is 7, which is a distance of 15 from node 5. Then 10, which is a distance of 20, and so on. We've already discussed all of this. So, and so the final one is whatever, 1, 2, 2, 5. 1, 2, okay, let's see, 1, 2, 2, 5, 5, 7, 7, 8, 7, 10, 10, 6, 6, 4, 6, 3, and 6, 9. Okay, really very simple, yeah, 6, in that order. Right? And of course, we can just draw a picture of it, same picture. Right? Very, very simple algorithm. And, right? Okay. Now, is there a linear programming? Can we do this through linear programming? Can we find this through linear programming? Someone should say yes, yeah. I'm waiting for someone to say yes. Yes, of course, yes. Why? Well, basically, what is the criterion here? Connecting, yeah. So, in other words, so what is the criterion? Yeah, it's not the path actually. It's not the path, yeah. So, what would the constraint be here? See, notice, for example, node 6 has 4 connections, right? So it cannot be that only one of them is taken. If it's a path, then one has to be, so 1 entry, 1 exit type thing. But here, we cannot have that. So how should we model it? Maybe you can think about it a little. But it is, of course. This is also something that we can program through linear programming. Okay, why don't you think about this a little? How would we model it as to get a linear programming problem from it? Basically, see, of course, you're minimizing the weighted sum. That's the obvious objective. So just like what we did here, what we did in the shortest path problem, the objective function is the same. But how to model the constraints is the challenge here. So think about it a little. Basically, you have to make sure that there are no cycles. That's the main thing. Making sure that all nodes are connected, 1. So in other words, at each node, at least one of them has to be equal to 1. That's the answer actually. Okay, I gave away the answer. Right? Anyway, think about it in case you didn't understand the answer. But basically, all right. Basically, at each node, the sum of the arcs at the node has to be greater than or equal to 1. Right? Right? So, for example, at 1, x12 plus x13 should be greater than or equal to 1. Then x12, x12 and x21 are the same actually here. So x12, x25, x27, and x57 has to be greater than or equal to 1, like this. So that all of them become connected, and we take minimum weight. All right, that's the simple answer. Anyway, no problem. Okay, now since we're on the topic of networks, we'll talk about another type of network called the flow network. Anyone can think of an example of a flow network? A network where things are flowing. What's the obvious thing in Bangalore? Traffic. Okay. Now, what is the objective in traffic network? To have maximum flow, right? How to make sure that we can push as many cars through our roads as possible. Yes? And that's the same thing here. Right? The maximum flow problem. Of course, I'm not saying that by learning this we can solve Bangalore traffic. Bangalore people have to learn, not just us. Okay? Right. So there are many problems. But this is one simple type of, maybe you can try to apply it, but the problem here is this model that we're learning is single source. Oh, maybe we can try this as a project actually. But the classical maximum flow problem is single source, single destination. In Bangalore, of course, everything is a source, everything is a destination. So anyhow, but you can try it. Okay, so maximum flow problem is a very simple thing. It's concerned with determining the maximum volume of flow from one node called the source to one other node called the destination or sink. So we're trying to send as many units from the source to the destination as possible. Now, what is the constraint here? The constraint is the capacity of the network. Each node, each arc has capacities. We cannot drive as many cars as we want through a road, right? There's a capacity. Right? When a road gets congested, naturally flow will be slower. Okay? So each arc has a minimum arc flow capacity which limits the flow through that arc. And so the thing basically is identifying the bottleneck in the system. All right? So we may have lots of roads, lots of network, but the point is, if at crucial point, if the capacity is low, then whatever we have elsewhere, the capacity will get stuck there, or the flow will get stuck there. Okay. All right. So here's an example. Now, by the way, this also links with transshipment problem. Do you remember transshipment problem? This actually links with the transshipment problem. This is called capacitated transshipment. This is a general capacitated transshipment model. Anyway, so in transshipment also you can bring this in. Okay. So for example, let's look at this network here. So our source is 1. So we can go from 1 to 2, 1 to 4, 1 to 3. And then here we're allowed to move in both directions. Okay, so from 2 we can go to 4 and we can come back to 2 as well. So we have all these 2 ways. Some networks only have one-way route, some have multiple ways, and so on. So we want to determine what is the maximum flow from 1 to 7 that is possible to this network. Anyone can look at this and try to determine anything? Any lower limits or upper limits anyone can see? No, not one. Not one here. It's not that. See, we want how many units are passing through. It's no longer binary. We want to see how many units we want. So it's no longer binary. It's integer value, but no longer binary. Right? So, for example, from 1 to 2, we can send up to 4 units. We can send 4 if we can. But the problem is somewhere else it may get stuck. See, for example, from 1, if we just look at these 3 here, from 1 we can send 4 plus 4 plus 3. That's how much? 11. So that's a constraint because the problem is we cannot exceed these capacities. But the problem is on the other side, if we look at 5, say 7, 4, 7, and 6, 7, the total there is 2 plus 3 plus 5, which is 10. So even though we can send 11 from this side, it can only admit 10 from that side. So those are 2 of the constraints. In fact, there may be some even further constraints in between as well. Okay? So how to identify the bottleneck is the real challenge here, as we'll see. Okay? I think, in fact, I think this 1 is a big bottleneck here. This will be a bottleneck surely, right? Oh, no, may not be. 3 plus 1, okay. 2, 3, okay. Never know. Let's see. All right, so how do we model this? Okay, first let's see what they're saying. Yeah, a capacitated transshipment model is developed for this maximum flow problem. Now, basically, what we're going to do is the following, all right? So, we're looking at how many units can go from 1 to 7, okay? So what we'll do is, we'll send all those units back from 7 to 1, okay? So we'll join 7 back to 1 through one arc and make it into a conservative system then. Okay, so that will make it into a conservative system. And that is the flow, that is the total system flow, okay? So we add an arc from 7 back to node 1, which represents the total flow through the network. And this has no capacity, and this is 7, 1, and that is actually what we're trying to maximize. That represents the objective. What we're trying to maximize is the flow from 7 back to 1, which is the flow in the system. Now, once we do this, now it's conservative. So at every node, then whatever comes into that node must go out. So here, x71 is equal to x12 plus x13 plus x14. Okay? Here, be careful. So, for example, at node 2, x12 plus x42 plus x52 equals x24 plus x25. At node 3, x13 plus x43 equals x34 plus x36, and so on. So, and in addition to all those node constraints, there are also constraints for each of these. So x12 is less than or equal to 4. x13 is less than or equal to 3. x14 is less than or equal to 4, and so on. Okay, so we'll have a large number of constraints. All right, let's do it and see. Okay. Oh, this is a different. Actually, it would have been nice to have the same picture as this. This would have been nice, but then it's non-directional. So, because we had already done it anyway. All right. So everyone is ready. So what do we have? Let's see. Okay, So this x71 I'll just call as Z. Right? We'll call that as Z, which is the objective. So the flow is Z. Okay, so I'll call that the first variable I'll type is that. Okay, Z. And then x12, x13, x14. Okay, that minimum has to be there. x12, x13, x14. Then x2425. Okay, x2425, x24, x25. Okay. Then x3436, x34, x36. Okay. Then x42, x43, x45, x46. x42, x43, x45, x46. Too many of them, huh? x42, x43, oh sorry. x43, x45, x46. What did I do? x45, x46. Okay, so that is done. X4. Then x52, x54, x57. x52, x54, x57. Okay. x47 is also, oh, sorry. Okay, I'll have to put it here, x47. Yes, thank you. Okay, x57 is there, right? x57. Then x64, x67, x64, and x67. And that's all, no? X6, that's wrong, right? And I put Z at the beginning, so this too, okay? So that Z is X71. Okay, so good, we're ready to do it. And total system flow is Z. This is what I want to maximize. So no need to. And then I need to do this for all the nodes. Node 1 to node 7. Okay. And then each arc. So what I'll do is just copy these. Why type them all out again? I'll copy these in transpose here. Okay. Right. So how many constraints? 24 constraints. Huh? Well, that's nice. Okay, so node 1. So again, incoming inflow minus outflow. Shall I take inflow minus outflow or outflow minus inflow? Inflow minus outflow. Okay, so at 1, inflow is Z, outflow is 1, 2, 1, 3, 1, 4. Yes? Inflow is Z from 7 to 1, Z. Outflow is 1, 2, 1, 3, 1, 4. Yes? So that becomes 1, minus 1, minus 1, and minus 1. Okay, very simple one. Okay, now at node 2, what is the inflow? Let's have a look. At node 2, inflow is X12, 42, 52. Outflow is 24, 25. Okay, so inflow is 12, 42, and 52. Outflow is 24 and 25. 24, 25. Yes? Now, node 3. Okay, 1, 3. Oh God, let's look at the picture. 1, 3, 4, 3. 1, 3, and 4, 3. 1, 3, and 4, 3. Outflow is 3, 4, 3, 5. 3, 4, 3, 5, right? 1, 3, and 4, 3, 3, 4, 3, 4, 3, 3, 6, huh? Yeah, sorry, that's 3, 6. I'm sorry. Read it properly. Okay, now node 4. What is node 4? Well, I can see one inflow here. 3, 4. 2, 4 is also there. 3, 4 is also there. And then 4, 2, 4, 3, 4, 5, 4, 6, 4, 7, huh? Okay. A lot of outflow here. 4 something. Yeah. Okay. All right. Okay. Now node 5. Okay. Node 5 is, it starts here. This is an inflow here. 2, 5, 4, 5. Okay, that's all, no? 2, 5, 4, 5. And outflow is 5, 2, 5, 4, and 5, 7. Okay, then node 6. What is node 6? Inflow is 3, 6, 4, 6, and 6, 4 outflow. 6, 4, 6, 7. Okay. Then node 7. Node 7 outflow is Z. Inflow is 4, 7, 5, 7, and 6, 7. Okay. All right. Now we need an identity matrix here. So identity comes on the diagonal. Oh, further. Okay, that's all. Yeah, that's the last one. Okay, so, oh, wait, there's one more. Yeah, that's all, no? Okay, and now we can do this. So, sum product. Oh, okay, so, oh, okay, and we fix these. All right. Okay, so first 7 are equal to, right? Uh-oh. First 7 are equal. Then these are all less than equal to, right? Yeah, less than equal to. Okay. Okay, less equal to 0, right? Everywhere it's equal to 0, right? Because we've made it into a conservative system. Okay, so we made it all equal to 0. Now less than equal to the capacity. So 4, 3, 4, 4, 3, 4. Okay, 4, 3, 4. Then what comes next? 2, 4, 2, 5. Okay, 2, 4, 2, 5. 2, 4 is 2, 2, 5 is 3, 2, 3. Next one is 3, 4, isn't it? 3, 4, 3, 6. 3, 4, 3, 6. 3, 4 is 2, 4, 2, 5. 4, 3, 4, 2, 3. Yeah, 2, 3. Yeah, 2, 3. Yes. Then 3, 4 is 3 and 6, right? 3 and 6. Yeah. Yeah, 3 and 6. Okay, 3 and 6. Okay. Next one is 4, 2, 4, 3, 4, 2, 4, 3, 4, 5, 4, 6, 4, 7. 4, 2, 4, 3, 4, 5, 4, 6, 4, 7. Okay. 4, 2 is 3, 5, 3, 5, 3, 1, 3. 3, 5, 3, 1, 3. Yeah. 3, 5, 3, 1, and 3. Okay. And next one is X 5, 2, 5, 4, 5, 7. 5, 2, 5, 4, 5, 7. 5, 2 is, okay, 3, 4, 2. 3, 4, 2. 3, 4, and 2. Now, next one is us 2 that are 6, 4, 6, 7, right? 6, 4 is 1 and 6, 7 is 5. 1, 5. Okay, 1 and 5. Okay, so let's see what happens. All right, so here is a Okay, everyone has understood how we develop the constraints? Oh, what happened? Why didn't it turn green? Okay, all right. And now we're ready. This time we're maximizing the flow, right? So maximum flow, variables are these. And constraints, first 7 are equal to these 7 here. And next ones are less than equal to. Unequal, oh, I see. Less than equal to, okay, yes. And simplex, and we can solve. Okay, so what is the maximum flow? As we suspected, 10. Okay, so we have said now that on this side, the bottleneck is at the right side here. So 2 plus 3 plus 5, whatever we have capacity on the left side, at the right, at the very end, there are only 10 units that can go in. So that becomes the bottleneck. Okay, that becomes your. Yeah. Okay, so, all right. Okay, so this is a capacitated transshipment problem. So we add an arc and then we maximize the flow over this arc, and this is the one. Okay, there's a variable for every arc, constraint for every node, flow out must equal flow in, and there's a constraint for every arc, that is, except arc capacity cannot be exceeded. Objective is to maximize the flow. Okay, now this is the same way of writing that. Maximize x71 or maximize z subject to summation I xij summed over I, that means all amount entering into node j equals summation ji, summation ji, no, should have been jk, summation jk summed over k actually, the misprint. Xi less than equal to capacity Cij, Xij, okay, so, all right, so LTP formulation in this case gives us how much? Optimal solution. Okay, so total is 10. So from here, 3 units, 4 units, and 3 units. That's 10. So from here, this 3 units splits us 2 and 1 here. 1 and 4 join in here to make 5. So from that 5, 1 goes here, 1 goes here, and 3 go here. So then 3 also come from here. Well, 3 plus 1 is 4. So that 4 units go from 3 to 6. It's joined by 1 more unit. So totally 5 units flow from 6 to 7. And on this side, this 2 units just continues. Okay? Right? So very, very simple. All right. So everyone has understood these various network methods. Actually, we're slightly behind. I thought we had to finish this last time. I'm sure we didn't finish it last time, huh? Okay, this is, okay, well, sad but true. Anyway, so, all right, our next topic, which I plan to start from the beginning, is called multi-criteria decision making. Where is it? Multi-criteria decision making, yeah? Let me see, it's not there, no? It must be at the bottom here. Oh, there it is. Okay, multi-criteria decision making. Okay. Okay, so as you can tell, it's a little more advanced than what we've been doing. So now, so far, we've seen many applications of linear programming. In fact, in a sense, this whole course is mainly about linear programming, as you'll see. But there are some variations and there's some extensions that we have to discuss. And the first basic problem is, if you remember, in linear programming, there's only one objective function allowable. But is that true about decision making? There's only one objective in decision making? The answer, of course, is no. Whenever we make decisions, we have to think of many, many different things. So never, in fact, it's never the case that there's a single objective. So what do? Well, there are various things that can be done, and one of them is what is called goal programming. That's the first thing that we'll discuss, how to bring in multiple objectives into our into linear programming. Actually, that's, and then there are various other things. So those are in the case of continuous types of variables. In the case of discrete variables, where we have specific choices to be made, there we can bring in what are called scoring models. And there's a lovely systematic way of developing scoring models through something called the analytic hierarchy process, which is gaining a lot of popularity nowadays, because earlier, of course, it was thought that, okay, what we'll do is we'll just take a single objective and make that, or the most important objective, we optimize, and the others we can sort of manage, that type of thing. But the goal programming approach, as you'll see, gives a way of or sequentially looking at objectives, sequentially, or taking weighted objectives. That is basically what is done there. Okay, so more and more nowadays, in fact, in finance, for example, nowadays there's a whole literature on how to bring in goal programming into finance. So, for example, a portfolio problem, you have, that's the most classic problem, return and risk, and how to prioritize that, how to go about managing both together, and that becomes a main application of goal programming, for example, in finance. Anyway, so let's quickly talk about this. So goal programming may be used to solve linear programs with multiple objectives, with each objective viewed as a goal. So the idea here is, when we have multiple objectives, the objectives become constraints. So we embed those objectives into constraints, and then we get what are called deviational variables. Deviation variables, okay? So what we do is, we have our objective and we set it equal to a target. Okay, we're trying to get a target. So the positive deviational variable means overachievement of the target. The negative deviational variable means underachievement of the target. Now, in some cases, we want to overachieve. So, for example, if the target is a profit, we want to overachieve that. So the positive deviational variable is good. The underachievement is not good. So we want to somehow minimize the underachievement there. On the other hand, if the target is to do with cost, we don't want to overachieve the cost. That means going over the cost or over the target. We want to underachieve it. So there, the underachievement is nice. Overachievement is what we want to try to minimize. Like that. So basically, we're converting objectives into overachievement and underachievement of a particular target or goal, and we want to see how to minimize overachievement or underachievement depending on what the context is. Okay, so basically the D1, D plus and D minus are acting like slack and surplus. Slack is like underachievement, surplus is like an overachievement, and so those are what these things are. And what we want to do is, we also want to bring in a priority sequence. So if one goal is more important, we'll handle that goal first, then go to the next priority, and so on. Okay, so second priority goals are pursued only after first priority goals are solved, and so on. Third priority goals after both first and second, and so on. Okay, so for each priority level, the objective function is to minimize a weighted sum of goal deviations. So at each level of priority, we see how many different objectives there are at that level, and we take a weighted average of the deviational variables there. And what we do is, once we optimize that, once we get an optimal solution to one priority level, that deviational variable is brought in as a constraint for the next level. So for example, if we're able to minimize, so suppose we want to minimize overachievement. So the first thing, suppose, is cost. So we want to minimize overachievement of cost. So let's call that D1 plus. So the first goal is minimize D1 plus. If that's already achieved, then we put D1 plus equal to 0 as a new constraint, and then try to get to the second level goal, and so on. Anyway, as we do it, we'll see how that works. Yeah. So this is the approach. Step 1, decide the priority level of each goal. So we have the different goals. Which one is most important, next most important, next most important, and so on. So there could be multiple priority levels, or they could all fall in the same priority level. Depends. Okay. Now, decide on the weight of each goal. If at a priority level, more than one goal is there, then for each goal, decide the weight WI to be placed on the deviation, DI plus or D minus from the goal. So depending on how important one particular goal is to another, we give a weight. So for example, if one goal is twice as important as another goal, then that gets a weight of 2. 2 is to 1. And set up the initial linear programming problem. So minimize weighted average of goal subject to functional constraints and goal constraints. Solve it. Okay, so solve this. So if there's a lower priority level, we go on to step 5. Otherwise, this is the optimal solution. What is step 5? So consider the next lower priority level goals and formulate a new objective function based on these goals. Add a constraint requiring the achievement of the next higher priority levels to be maintained. So for example, if at priority level 1, this was so W1 D1 plus W2 D2 minus. Suppose that is achieved at level K. Okay, suppose that is achieved at level K. Then bring in this constraint before minimizing the next one, and so on. And we keep on doing this until all priority levels are over. Okay, so here's a simple example. Okay, conceptual products. Maybe I'll sit down for this. Legs are aching a little actually. All right, conceptual products is a computer company, produces CP400 and CP500 computers. Okay, the computers have used different motherboards produced in abundant supply to the company, so that means that's not a constraint, but use the same cases and disk drives. Okay. CP4 model uses 2 floppy disk drives and no zip disk drives, whereas CP500 uses 1 floppy disk and 1 zip disk. For those who don't remember, floppy was floppy, okay, whatever, anyhow. It was a type of storage device. Maybe we should update the problem, but anyhow, it doesn't matter. Old timers will remember this. Okay, so the disk drives and cases are bought from vendors. There are 1,000 floppy disk drives and 500 zip disk drives available with us, and 600 cases. Okay, so these are functional constraints. These are real constraints in the problem. Now, it also takes 1 hour to manufacture CP400, and its profit is $200, and it takes 1.5 hours to manufacture CP500, and its profit is $500. So much more. Okay, now come the different objectives. What are the different objectives? Well, here are some. Okay, there are 4 different priorities, 4 different objectives. So, meet a state contract of 200 CP400 machines weekly. So, we have to deliver at least 200 CP400 machines to whatever, to some client. Next priority is make at least 500 total computers weekly. So at least 500. Then make at least a revenue of 2,50,000 weekly. That's goal 3. And then use no more than 400 man hours per week. Right? So, okay. So, our first is to meet that state contract and so on and so forth. So how do we formulate this? Well, first of all, the variables are the number of CP400 computers we produce. X2 is the number of CP500 computers we produce. And then we have the deviation variables for the goal. Di plus is the amount, the underachievement of goal I, and Di plus is the overachievement. Di minus is underachievement. Di plus is overachievement. We'll see where they come in. Now, the functional constraints are about availability of disk, floppy disk drive, this zip disk drive, and cases. So, 2x1 plus x2 less than equal to 1000. That is, remember, CP400 had 2 floppy disks and CP500 had only 1. Whereas zip disk is only used in CP500, so x2 is less than equal to 500, and all of them have use cases. So x1 plus x2 less than equal to 600. This is a simple one. Okay, next one. Now, where are the goals? First of all, we have to produce at least 200 CP400 computers weekly. So, write that as x1 equals 200 with deviational variables. So, x1 plus d1 minus d1 plus is equal to 200. Now, why are we adding d1 minus and subtracting d1 plus? Okay, so underachievement means is like a slack. So, see, if I am not able to meet 200, suppose it's 150, then it's underachieving by 50, and so that's why by adding 50 to it, I get 200. On the other hand, if I overachieve, if I make 250, that's exceeding 200 by 50, and so when we subtract 50 from that, that equals 200. And so, underachievement is added to the left-hand side, overachievement is subtracted. It's like the idea of slack and surplus. Okay. Next one is total number of computers. That's x1 plus x2 plus d2 minus d2 plus equals 500. Now, what about the profit? The revenue actually it is. Okay. Oh, this is 200 x1 plus 500 x2 plus d3 minus d3 plus equals 250,000 or 250,000. I'm multiplying by 1,000 by 1,000. Okay. 7,000. Oh, that's another important thing in this. See, when we're okay, we'll talk about it when we come to that. Okay, we'll talk about it later. See, we divided by 1,000 here, right? We'll talk about what the implication of that is. When we're combining, or we're weighting, we'll see. Okay, now, last one was total man hours required weekly was x1 plus 1.5 x2. We want that to be equal to 400. So plus d1, d4 minus, plus d4, minus d4 plus. And of course, all our variables are non-negative. Okay, so we want to. So what do we do first? Well, don't forget there's a priority level. So first priority is to meet the state contract of 200. So in other words, if we want to meet this, what is more important, overachievement or underachievement? No. Now see, the objective has to be put in terms of minimizing of the deviational variables. So which one do you want to minimize? D1 plus or D1 minus? D1 minus. No, you want to minimize D1 minus because if it shouldn't be underachieved. That's the basic idea. So we don't want to underachieve, and so we should minimize D1 minus. I know it's a bit confusing to start with, but so whatever you don't want to do, you minimize. Okay, that's the basic idea here. Okay, so to start with, we minimize D1 minus. So we don't want to underachieve. On the other hand, we want to we want to achieve at least 50 total computers. Again, minimize the underachievement there. So minimize D2 minus. We want to make at least 2,50,000 of us. Again, minimize D3 minus. And here, we don't want to overachieve the number of man hours. So here, minimize D4 plus. Okay? So, yes or no? Everyone has understood, right? So basically, in other words, see, if we had written them as constraints, we'd have said x1 greater than or equal to 200, x1 plus x2 greater than or equal to 500, whatever 200 x1 plus 500 x2 greater than or equal to 2,50,000, and here x1 plus 1.5 x2 less than or equal to 400. So where it's less than or equal to, overachievement is being minimized. Where we're writing greater than or equal to, underachievement is being minimized. Okay, that's the idea. Oh, can we minimize this also? Yeah. Why is he turning on his? What? Okay. By mistake, probably. Okay. Anyway, no problem. So finally, we write it like this. Okay, this is how it's written. P1 D1 minus, P2 D2 minus, P3 D3 minus, P4 D4 plus. So what you're minimizing at each stage, and P1, P2, P3, P4 represents the priority levels. If there are some at the same priority level, what weights we're also putting, we have to put there. Yeah. Okay, and functional constraints, 2x1 plus x2 less than equal to 1,000. x2 less than equal to 500, x1 plus x2 less than equal to 600, then x1 plus, these we've already discussed, so we just put them, it's all just putting it together. No, see, that's fine. See, if they were all at the same level, then it will be written as P1 and weights for all four. Then you'd have to put weights for all four. Okay, now, perhaps since you asked this question, let me also tell you about this weights thing. The problem here is, for example, okay, see, for example, this constraint that we've written here, right? We could have written this as 200 x1 plus 500 x2 plus d3 minus d3 plus equals to 2,50,000. But then the problem would be that, see, if we had written it like that, d3 minus and d3 plus would be in actual rupees. How many rupees we're going over and under, or dollars in this case, whatever. Okay. Now, what depending on, so for example, if we look at the next one, which is labor hours. Okay. So D4 minus and D4 plus is in how many man hours or labor hours are excess. Now, when we take weights, therefore, we're comparing labor hours with rupees or dollars or whatever. So the weights have to also reflect what units we're taking there. So the way they've written it, for example, is 0.x1 plus 0.5x2 plus 0.2x1. Now D3 minus and D3 plus are in thousands of dollars, whereas D4 minus D4 plus are in actual labor hours too. So the weights have to reflect the units that are being used. That's the important thing there. Not that, okay, this is 2 times more important than that. Not only should that be in there, but you should also take the actual units into account as well. Okay, so that's one danger that you have to be careful of there. So, for example, if you're just looking at in terms of how important one constraint is with respect to, or one goal is with respect to another, the problem is if one goal, the overachievement, underachievement is in lakhs, whereas another goal, the thing is only in units, then of course that one will weigh more. Okay, so the problem is, so even if the importance, so what basically you have to do is look at importance as well as the units that are involved. And so often we try to standardize the units and then give weights according to importance. Okay? All right. So in other words, actually one application that I had done was when we take targets, we make the target equal to 1 in all cases. So divide it so that it becomes equal to 1, and then bring in the deviational variables, and then sort of, so that's another way of doing it, so that the importance is maintained. But then it also could depend on what 1 unit of labor versus $1 profit, how to trade that off. So again, depending on the application. So there are practical problems in that. You have to keep on trying or taking different weights and seeing which one is most suitable. So in a sense, there's partly a little trial and error to see how to balance the weights in a proper way. Okay. Anyway, that's for much later. When you start applying it, you'll start seeing some problems happening there. Okay, so I think they're going to try to do a graphical solution. We'll do both. So first, let's understand what is done graphically. So the first graph is, of course, of the functional constraints. Okay. Okay. So to solve graphically, first graph the functional constraints, then graph the first goal, x1 equals 200. Note that in the next slide, there's a set of points that exceed x1 equals 200. Okay, so we started with the first goal, first constraints, which is, this one is x1 plus x2 is less than or equal to 600. I'll just use the pointer here. Okay, so these are the constraints. First constraint is x1 plus x2 less than or equal to 600. Here 2x1 plus x2 less than or equal to 1000, that is the floppy disk constraint. And this constraint is x2 less than or equal to 500, zip disk constraint. Then we put in the first goal, which is x1 greater than or equal to 200. So ordinarily this would have been our feasible region, right? So from here to here, right? This would have been the feasible region. When we put in the first goal, x1 greater than or equal to 200, now the feasible region shrinks to this. Okay. Now, amongst these, we want to next look at the next level. What is our next level? Our next level is to bring in goal 2, x1 plus x2 greater than or equal to 500. So within that, we have to take x1 plus x2 less than or equal to 500, which I think will be a line like this, parallel to this line, but going through 500. And it will be greater than that. So it comes like this. So this line is x1 plus x2 equals 500. And since it has to be above that and to the right of this, so now we have this region here. Then we bring in the third goal. Right? What was the third goal? Third goal was to do with profit. Okay? Or profit or revenue. Okay? So now this next goal is 0.2 x1 plus 0.5 x2 equals 250. Now, unfortunately, none of the points in this region satisfy this. So what we do is we look for the closest point to that. Okay? So note that no point satisfy the previous functional constraint and this new goal. Okay? So thus, to minimize D3 minus, the minimum value is achieved at the closest point to this, which is at x1 equals 200, x2 equals 400, and so, and this is when point x2 equals 2,500, 2,40,000, and so the deviation is 10. So that happens at this point here. So when we put in this goal, 2x1 plus 0.5 x2 equals 250, this is the line. The closest point is this, so this is our solution. So x1 equals 200, x2 equals 400. And, okay, so now, when this is done, why do we not go to the next level? Because already we're not satisfying this, so there's no question of going to next priority level. The moment you cannot satisfy a particular priority level, we stop there. That's the final solution. Okay, shall we do this in Excel also? Okay, so let's go back to our problem here. Okay, this is the problem. So what do we have? Okay, so x1, x2, d1 minus d1. Okay. All right, so x1, x2, d1 minus, d1 plus, d2 minus, d2 plus, d3 minus, d3 plus, and D4 minus D4 plus. Yeah? Okay, so these are the variables that we have. Okay, and what is our objective? Well, that's what we're going to decide last. And generally, in linear programming, we write down the objective first, but no, that's what we'll write down last here. So first we write down the functional constraints. Okay, functional constraint 1. Functional constraint. Okay, we'll just call it. Okay, doesn't matter what we call it. So what were the constraints again? 2x1 plus x2, then just x1 and x1 plus x2, right? All right, okay, so some product of variables with constraints, right? Okay, oh, all right, and these are the things here to be fixed. Okay, all right, and one here, these three, no, oh, sorry, start here. These 3 plus 4, 1, 2, 3, 4, right? So copy that here, and these are less than equal to constraints. Okay, these 3, and these are equal to constraints. I'll call this LEQ. Uh-oh. Huh? Where am I going? Oh, okay. Less than equal to how much? Well, 1,000. This was 500 and 600. No? Huh? Was that? 1,500, 600. 1,500. Okay. And these are 200. What was the next one? What was the next one? 500. 500. 500. Next one is 2,50,000. And last one is 400. Okay. Now, let's put with this. Okay, we'll call this a goal. Goal 1, 2, 3, 4. Goal 1, 2, 3, 4. Okay. Yeah, this is goal 1. Yeah. And these are functional. Functional 1, 2, 3, 4. 1, 2, 3. Functional 1, 2, 3. Okay. All right. Okay, that's nice. All right. Now goal 1 was just x1. Goal 2 is x1 plus x2. Goal 3 is 200 and 300. No, 200, 500, sorry. And goal 4 is 1 and 1.5. Okay, and then we have the, so it's plus D1 minus, minus D1 plus, plus D2 minus, minus D2 plus, plus D3 minus, minus D3 plus, and plus D4 minus, minus D4 plus. Yeah, very simple. And, oh my God. And to start with, if you remember, what are we minimizing? D1 minus. Okay, we're minimizing D1 minus. That's the first. Okay, and so we start with this constraint. So this is our objective, to minimize D1 minus. Subject to what? These are less than equal to, oh, sorry, what am I doing? These are the variables. Sorry, I'm sorry. Okay, these are the variables. What happened? Is there any video? I cannot see anything. Huh? Cannot see anything. I'm sharing. Stop share. Oh, I see. Who is that? I don't know. Anyway. Okay. All right. Just check. I don't know. All right. We will see. Okay. So, what happened? It's yeah. Of course, it's fine. Okay. So what were we doing? So we're minimizing this thing, right? What was that? Objective. The objective. Right place. Yes. Now we need to add in the constraints. What happened? Okay, constraints are here. These are less than or equal to these three. And now we add in these goal constraints as equal to. These are equal to these. Okay? And the first one, of course, is to minimize that. Minimize the first D1 minus. Okay? So let's solve. And this is our first thing. So D1 minus is 0. D1 minus is 0. And we have 200, 400, which will be the final solution, of course. Okay. So first one, D1 minus is 400. D1 minus is 0. Okay. So next thing, what do we do? Now we're going to put in D1 minus. So D1 minus as a constraint. So where is D1 minus? That is D1 minus. So the next constraint is that D1 minus equals 0. So once we finished priority level 1, we bring in this new constraint, and now we go to priority level 2, which is D2 minus. So now we want to minimize D2 minus. So solve, but we bring in this new constraint that D1 minus equals 0. D1 minus equals 0. And we solve again. Alright? So by chance, it's already achieved at the same point. By chance, all of this will be achieved at the same point. Okay? So our next constraint is what? Try to achieve D3. Okay? So now we put in D2 minus as another constraint. So D2 minus, okay, again equals 0. Okay, in fact, we can just copy this entire thing down. And so now D2 minus is taken out of this, and D3 minus is what we want to minimize now. D3 minus. Okay, so what is it? This single one here, I'll now change to this and this and this and this. Okay, I'll solve it, but it's wrong because this should be 0. Okay, and we'll solve it again, and it's again minimized at D1 at D3 minus is 1 10,000. Okay. So what do we do now? Well, this is our final solution because we cannot bring D3 minus down to 0, and so this is our solution. So what is our solution? Same thing as what we got earlier. So x1 equals 200, x2 equals 400. We're achieving level 1 and level 2 priority goals, and we're minimizing the underachievement of level 3 priority goal at 10,000. We're 10,000 short of the profit target or profit or revenue target. Okay, so very, very straightforward. Okay. Okay, shall we do one more of these? There is, okay, there's a nice one here in the textbook that we'll quickly go through. That one has a weighted average. Okay, so that one is a little more interesting. Integer, multi-criteria. Anyone can see this one, multi-criteria. Okay, multi-criteria. 100%. Okay, so problem here is, yes, okay. Okay, this is the problem. This. Okay, so here. All right, so let us consider a problem with some investment advisors. A client has $80,000 to invest, and as an initial strategy, would like the investment portfolio to be restricted to 2 stocks, US Oil and Huber Properties, Hub Property or whatever that is. The price per share is 25 and 50. Estimated annual return per share is 3 and 5. And the risk index per share is 0.5 and 0.25. So US Oil, which has a return of $3 on a $25 share price, provides an annual rate of return of 12%, whereas Hub Properties provides an annual rate of return of 10%. Risk index is 0.5 for US Oil and 0.25 for Hub Properties. A rating that, whatever, higher rating index implies greater risk, whatever. Okay, doesn't matter. Okay, so the risk index may vary from 0 to 1600. Okay, so the client would like to avoid a high risk portfolio, and therefore US Oil would not be desirable. So the maximum total risk index is of 700 is what they're saying. So considering only risk, one goal is to find a portfolio with risk index of 700 or less. Okay. Another goal is to obtain an annual return of at least $9,000. So in portfolios, that's the thing. Risk versus return, as I was saying in the beginning. Right? This goal can be achieved with a portfolio consisting of 2,000 shares of US Oil and 600 shares of Hub Properties, whatever. Annual return is 9,000. However, the portfolio risk would be high, 1,150, and blah, blah, blah. Okay, so the portfolio is a multi-criteria problem. So the top priority is to restrict risk. Keeping the portfolio index of 700 or less is important. Is not willing to trade this achievement for any amount of increase in annual return. So that's the priority level 1. Priority level 2 is find a portfolio that will provide an annual return of at least 9,000. Okay. Priority level 2 goal. And that's all, huh? What happened? There was one with. Okay. I'm pretty sure that we solved one with. Okay, all right. This is not a very interesting one. There was one with multiple. What was the one next after this, huh? Here they had one. Yeah, see, this one. Okay, maybe we'll do this one then. Oh, we're running out of time also. Okay, so anyhow, okay, since we started talking about that, let's finish it. Okay, so what do we have here? So our basic problem or the basic constraints are as follows. Okay, so 25U plus 50H less than equal to 80,000, that's the investment. and the risk target is this 0.5U plus 0.25H minus D1 plus D1 minus is equal to 700, the risk index, and the return constraint is 3U plus 5H minus D2 plus D2 minus equals 9. And the first thing is our primary goal, which is risk, which we want to minimize overachievement of risk. So D2 plus. No, sorry. D1 plus. That's the priority 1. Okay. Minimize D1 plus. Okay. And after that, we want to minimize underachievement of profit. So D2 minus. So D1 plus and D2 minus. Okay. In the first one, what is it? Here is our feasible region. So feasible region is with 25U plus 50H less than equal to 80,000, which is under this here. Then if we do our first, whatever it was, first priority is the risk. So that means 0.5U plus 0.25H less than equal to 700. So that will cut out this slice here. Okay. Okay, here is the slice here, which is 0.5U plus 0.25H less than equal to 700 here. So this becomes our feasible region that satisfies the first goal. Okay, and then we have to find the one that minimizes D2 minus. So we want to find the one that minimizes D2 minus, and that is this equation here, right? Priority level 2 goal, which is this equation here. And again, we want to find the point that is closest to this, right? So D2 minus is, I think this point will be the closest. U equals 800, H equals 1200 is the best solution for the secondary goal that does not degrade the solution from the primary goal. So out of the points satisfying the primary goal, we find the one that is closest to the secondary. Okay, so that leads us now to, okay, there's this one, but no, I think we'll, okay, but don't worry, we will quickly do that because the more important thing for us next is, okay, scoring. Okay, so let's do one simple scoring model. Okay, so now a scoring model basically is a way of looking at finite number of alternatives. So the type of thing that we looked at earlier was continuous variables. On the other hand, when we have finite number of alternatives and finite number of criteria, we can use some type of scoring. And to illustrate this, we're going to look at a model for job selection, scoring model for job selection. So suppose a student with a double major in finance and accounting has received the following 3 job offers. So a financial analyst for an investment firm in Chicago, an accountant for a manufacturing firm in Denver, and an auditor for a CPA firm in Houston. So which one should they select? Well, it depends on different perspectives, okay? So what are some of the perspectives that we look at here? Salary package, okay. So which one offers a good salary package? What other thing? Yeah, location. So some locations may be more preferred than others. Maybe it's something that's closer to home or something. Yes, anything else? The type of firm also maybe. Yeah? Maybe the type of job, the type of firm also. Big reputable firm, different industry also matters. Like this, okay? So many criteria can be there. Okay, so the student has made the following comments. The financial analyst position provides the best opportunity for my long-run career advancement. That's another criteria. Then I prefer living in Denver rather than Chicago or Houston. Maybe his girlfriend stays something like that. I like the management style and philosophy at the Houston CPA firm the best. So clearly there is multiple criteria here, and somehow we have to, okay, so considering only long-term career advancement, the financial analyst position in Chicago is the best. Considering the location criterion, accountant position in Denver, and considering the style, auditor position in Houston. So to make it more difficult, all of them are desirable in some way or the other. Okay, now how do we do this? Well, we list out all the decision-making criteria. So what are all the criteria we have to consider? And we assign a weightage to each of these. So which one is more important, which one is less important? Could be from 1 to 10 or something, it depends so how you do it. Then rate how well each decision alternative satisfies each criterion. Again, rating from 1 to 10 perhaps. Then compute the score for each decision alternative by taking a weighted average or a weighted total and order the decision alternatives from highest score to lowest score. The alternative with highest score is the recommended alternative. A very rough model, as you'll see. Okay, so the model is like this. SJ, the score is summation WI RIJ, where WI is the weightage or importance given to the ith criterion, and RIJ is the rating of the ith criterion for the jth alternative. Okay. So, for example, here are the criteria: career advancement, location, management, salary, as someone has said, prestige, job security, and enjoyable work. These are the criteria that that particular student has come up with. And the rating importance scale is from 1 to 5. 1 is unimportant, 5 is very, very important. You can use other scales also, 7 point, 9 point. Yeah. But usually it's an odd number of points. Yeah. Now, so career advancement is considered very important, so given a weightage of 5. Location is average, so maybe around weightage of 3. Management is somewhat important, so 4. Salary, again, average 3. Again, it varies. It's a subjective thing, as you can see. Some people will put more on salary, perhaps. Prestige, not so important, so 2. Job security is important for that particular student, so 4. And enjoyable work also is very important. Very difficult to work in a job that's not enjoyable. Okay, so 5. Okay, so now for the other one, we're giving a rating of 1 to 9. So you could, again, it varies. You can use 9 point there also, you can use 5.0. Okay, so extremely low is 1, extremely high is 9, and average would be around 5, would be 5. Okay, so here are the ratings for each of them. So analyst in Chicago, rating 8 in terms of career advancement, 3 in terms of location. Here, Denver is preferred location. Management style, Houston auditor is preferred. Here it's not that much. Salary-wise, again, preferred is Denver. This is also okay. Prestige-wise, this is better. Job security-wise, Denver is better. And enjoyable work-wise, again, that is better. Okay? So it looks like career advancement. So, yeah, in terms of career advancement, okay, prestige as well as enjoyable work. Chicago is better. At this level, this is better here. Location, salary, and job security. And here you have management. That's the only one there. All right. So what do? We multiply weightage into the rating and take the total. You can also divide by the weighted average. You can also take, but this same thing, you'll get the same thing. So take the weighted total, and so our score for Chicago is 157. For Denver, it's 167. Denver is 167, and for Houston is 149. So which one is the preferred alternative? Clearly Denver. Okay. Now notice when you look at the contribution to the score, under 4 headings, actually, Chicago is better, but the total weightage turns out to be so. It's not just the. Okay, so the accountant position in Denver has the highest score, recommended decision alternative. The analyst position in Chicago ranks first in 4 of the 7 criteria, compared to only 2 of 7 for the accountant position. So the weights, after looking at the weights, basically the Denver position is superior. Okay, and of course it's a sum product, just a sum product which we use in Excel. Okay? Sum product. Well, they've actually multiplied, not necessarily really. Yeah, so scoring calculation. Okay, now we have, let's see, unfortunately we have another class after this, right? Okay, so let's do this in our next thing. This is a nice, as you'll see, after looking at the scoring model, which looked a little arbitrary, this you'll see will give some type of structure to the way that we give scores. Okay, so we'll do this in our next class. Okay, I think we're slightly behind in schedule, so we'll catch up. Don't worry, we'll catch up in our next. Okay, so this is a nice thing. I'll just give you a quick preview. You end up looking at what are called paired comparisons. So you make paired comparisons. So when you make these paired comparisons, the consistency becomes better, or the scores that you get are more consistent in that way. See, the type of scoring that we did here in this scoring model, you tend to often get inconsistent scores. If you do this, just randomly give some. Whereas when you do this through paired comparisons, often, subject to certain consistency measures, you tend to get better type of results. So we'll talk about that analytic hierarchy process in our next class. Okay, right? It's an interesting approach. And then we'll go on to something called dynamic programming and dynamic programming and stochastic programming. Those are the last 2 modules. So please, of course, maybe I'll save this one also. Okay, yeah, let me stop recording.